Exercise 1.1 of Class 12 NCERT book. Questions on reflexive, symmetric, transitive, and equivalence relations. Give an example of a relation which is symmetric but neither reflexive nor transitive. Let's take an example. Set P consisting 4 elements A, B, C, D. Let's recollect. Any relation in set P is a subset of the Cartesian product of P, that is P cross P. P cross P is the set of all possible ordered pairs made using the elements of the set P. That is, pair AA, AB, AC, AD, BA, BB, BC, BD, CA, CB, CC, CD, DA, DB, DC, DD. 16 elements. 16 pairs in this Cartesian product of P. Now, any subset that we create is a relation from P to P. Any subset of this P cross P. Let's create a P cross P, a subset of P cross P as a relation satisfying these various conditions. First condition, we want a relation which is symmetric but neither reflexive nor transitive. Let's take, I'm taking this example, R, a subset I've created of this P cross P by choosing these two ordered pairs AB and BA and nothing else. Because we want the relation to be symmetric. To have it symmetric, the pairs of the form, whenever there is an ordered pair AB, its reverse BA should also be there. Only then the relation is called symmetric. We need not go for more elements. We need not put an AC and then CA and all. If there is an ordered pair AB, there should be BA. If there is no ordered pair AC present in the relation, we need not check for CA also. So, since we want to have an example, let's go by the minimum elements in the relation. First condition I have maintained. Now, we do not want it reflexive. To call it reflexive relation, there should have been the elements of the form AA. That is, AA, BB, CC, DD should have been included in it. All of them should have been included in it for this relation to be reflexive. If we choose one of them, if we keep one of them, say for example AA also to be included in it. Of course, by joining one of them it doesn't become reflexive, no problem. But it may go transitive. Be careful. Look, the pairs AB and B are there and the first and third element A and A is also present, which is the condition for transitivity. Now, if AA is kept, these two elements are following the transitivity condition, the first and third element AA happens to be there. So it's better not to keep that AA there for it to be not transitive. So what if we choose another one BB? Then also there is problem, because when the pair BA and AB are there, choose B as the first one, AB as the second one. Then comes the elements BB present. That also can lead to the transitivity. Hence, we avoid taking BB also. If you choose AA and BB both there in this relation, the relation would become transitive. So, we avoid taking them. So here, by choosing only these two elements to form this subset, we have maintained this relation symmetric, but neither reflexive nor transitive. Next, we want another relation, another subset of this P cross P, which is transitive, but neither reflexive nor symmetric. Here we go. To maintain it transitive, whenever there are pairs of the form A, B and B, C having the common element B, There should be element, the first and third AC should also be there. Yes, I've maintained it. That's why it's transitive. But if we do not want it reflexive, what we should do is avoid taking AABBCCDD, reflexivity. All the pairs of the form AABBCCDD are there. That's avoided. Now, of course, it's not symmetric. Why not symmetric? Because when AB element is there, BA is not taken. To be symmetric, for every pair AB, there should have been BA. If BC is there, CB should have been there. If AC is there, CA should have been there. None of them have taken, so it's not symmetric. Next, we want an example. A relation which is reflexive, symmetric, but not transitive. First of all, let's maintain it reflexive. To be reflexive, we need to keep all these elements A, B, B, C, C, D, D. Yes, maintained it reflexive. Now, for it to be symmetric, if you're choosing BD, keep DB also. If you're keeping AB, keep BA also, the reverse ones. So symmetry is maintained well. Symmetry, BD, DB, opposite, opposite, reverse. AB, BA, reverse, AB, then BA. But be cautious. At present, is it transitive also? Let's check. Here, BD and DB are there. To call it transitive, BB should be there. It's there. It looks transitivity is going okay. Let's go to this pair. AB and BA. Middle element same. So if AA is there, it will go transitive. Yes, it's there. It looks the relation has automatically become transitive. This pair is following the transitivity. This pair is following the transitivity. But it's not actually transitive. That is because look at those elements only in a different way. Take DB and BA. DB and BA are present in the relation. Now for it to be transitive, the element DA should have been also there, which is not found. Hence, this relation is not transitive. Next, we want an example which is reflexive and transitive but not symmetric. Of course, for it to be reflexive, all the elements of the form AA, place it. That is AA, BB, CC, DD are placed. Reflexivity is maintained. Now, we want it transitive. Okay. BD and DA. Then BA is also maintained. Transitivity okay. Then we do not want it symmetric. Of course, it's not symmetric. Why? I've kept BD but not DB. The reverse is not kept. Only if the reverse is kept, it will go symmetric. DA is there but AD is avoided. So symmetry is violated. But of course, this example is reflexive and transitive. But same time, it's not symmetric. Next, we want another example which is symmetric and transitive but not reflexive. Here we go. Not reflexive. I've kept AA, BB and CC. But I simply avoided one of them, that is DD is avoided. To maintain it not reflexive, one of them you avoid among those same pairs AA, BB, CC, DD. Among them DD is avoided. Now is it symmetric? Yes. For symmetry I have kept BD and DB reverse reverse, D and AD reverse elements, BA and AB reverse elements. So whenever there is a pair, its reverse element also maintained to keep it symmetric. Now lastly, is it transitive?